Okay, 9-6, being able to graph complex numbers in the complex plane and convert complex numbers from rectangular to polar. This is very similar to the work that you're doing in 9-3. So let's just take a second and briefly review the kinds of examples that you're going to be asked to do, the expectations here. So the complex plane is very similar to the real number rectangular plane in the sense that we define the complex plane having the horizontal axis here consist of just the real part of the complex number, and the vertical axis shown here representing the imaginary part of the complex number b. So now we can do a couple things with this. Let's take a look at an example of a number that's written in complex number written in rectangular form. So here you have two complex numbers here for example A and example B. Graphing, like we've said before, is just like your rectangular plane with real numbers here. If we were trying to plot the point z here at 3 plus 2i, we're going to go 3 to the right, and that's our real part, and then 2 up, that's our imaginary part. So there's z. Now absolute value is a distance value is away from 0. So if this is 0 here in our complex plane, we need to determine that distance that point z there is from 0. And you can see that to find the distance, it's a pretty simple trick with Pythagorean theorem. So to sum up here, to find the absolute value of a complex number, we just simply employ the Pythagorean theorem. A squared plus b squared would give us the absolute value. Alright, let's take a look at the other one. Let's first plot that point 4i. Treat 4i as a complex number a plus bi with the a portion missing. So if we're going to plot that point, that means we have a real value of 0 and an imaginary value of 4, which would put us right there. Coming up with the absolute value for this one's pretty simple. No Pythagorean theorem needed here. Remember, it's just a distance a value is away from 0. So if that's the distance that our value is away from 0 right there, indicated with the highlighted line right there, we have a distance of just simply 4. Now when we look at the other objective here in this lesson, which is being able to convert points, complex numbers from rectangular to polar and vice versa, we had to get a feel for where the polar form of a complex number actually comes from. Well, if we look at that right triangle right over here, we can develop a lot of conversions on our own. It's much the same way when we were back in 9-3, and we developed these conversions here. The only difference now going from 9-3 to 9-6 here is that every single x and y can just simply be replaced with a's and b's. Notice that now rectangular form, instead of saying xy, becomes now a plus bi. And one thing that we should pay attention to is pay attention to this little portion right here. Notice that a is equivalent to r times cosine of theta, and r is equivalent to b is equivalent to r times sine of theta, just like x and y were. We can take that concept and do some substitution with the complex number a plus b. So now a plus bi, with substitution, becomes r cosine theta plus r sine theta times I. And then if we look to see that there's a greatest common factor here, which is the r right there, let's factor that out and take a look at what we have now. Now we have r times the cosine of theta plus I times the sine of theta. So now what we're looking at here is what a polar form of a complex number should look like, which we can now abbreviate, and which we do very often because we have this happening in the parentheses every single time. We can just abbreviate that as just saying r cis theta. So let's do a couple of examples. So when you're looking to now take a point that's in rectangular form and convert it into a point that's in complex form, in polar form, realize you're just taking the stuff that was right here from 9-3 and just applying now the complex number scenario. So first move, let's get r, and let's use Pythagorean theorem to find r. Although if you examine this point carefully, notice that the a is -3 and the B is 4, so we'd be right here, and note that we would have a 3, 4, 5 right triangle. So that makes the R pretty easy to find. Now to find theta, well, we need to do inverse tangent. Now when you roll through inverse tangent, note that the angle that you get here is negative 53.1 degrees. Doing a quick quadrant check here with this here, note that if we have an R value of 5 and an angle of negative 53.1, that would put us in the fourth quadrant, which does not match the situation that we want here, which we want in the second quadrant. What we were actually given here, I've done this in class before, is we were given this angle right here of negative 53.1. So to get our true angle for theta, let's just add 180 degrees to it. That's more like it. So now we have 126.9 degrees, which is the angle that we want. And so now we can finish this off by writing our value as R in the form of the packaging of R cis theta. Okay, let's roll through another example. Alright, so this point here, Pythagorean theorem, let's find R. Alright, so let's go get theta using inverse tangent. So now let's write our point now in polar form. Alright, let's go in the other direction. Let's now take a point that's in polar form and let's express it now in rectangular form. One other thing they also wanted you to do here is to graph the point. Now when you see the formal way of writing the complex number in polar form, like you see here, 4 cosine of 11 pi over 6 plus I times sine of 11 pi over 6, we can write our shorthand notation here as just simply saying 4 cis 11 pi over 6. So it's just like plotting a point that's real. Go out to 4 and rotate to 11 pi over 6. So there's your point right there. So now what we have to do here is convert that point right there of 4 cis 11 pi over 6 and convert that into rectangular form. Recall from 9.3 we were doing this when it came to real values. Only now, instead of conducting our business with real numbers, now we're conducting our business with complex numbers, so the situation changes just slightly. So to go from polar now to rectangular, what we have to do to first is find our A value for A plus BI, which is doing R times cosine of theta. We can use a unit circle to determine that the cosine of 11 pi over 6 is nothing more than a positive square root 3 over 2. Simplifying this even further, note that when we have 4 times now the square root 3 over 2, we can just reduce those, and now we just have 2 times square root of 3. Let's go get B. So to find B now, instead of doing 4 cosine 11 pi over 6, now we're doing 4 sine 11 pi over 6. Unit circle, 11 pi over 6, that's going to be a half. In fact, it's going to be a negative 1/2 because now we're floating down there in the fourth quadrant, aren't we? So when we take 4 and multiply it by a negative 1/2, now we have negative 2. So now we can write our final answer, which looks just like this. We'll take the A value, 2 square roots of 3, and we take the B value, which is negative 2, and just put it in our packaging of A plus BI form. 2 square roots of 3 minus 2i. So there you have it, where you converted numbers from polar to rectangular. We also took numbers that were in rectangular form and we converted those into polar form. And we took a look at a complex number in rectangular form, we plotted it, graphed it, and were able to find the absolute value. So those were all the expectations here from 9-6.